Welcome, everyone. Today, I am presenting our work on a multi-port dual-band antenna designed specifically for modern multiple input, multiple output, or MIMO communication systems. This design targets the critical frequency bands utilized by Wi-Fi 5, Wi-Fi 6, and Wi-Fi 6E. I will walk you through our approach, which leverages a single-layer architecture to achieve independent band control, and show how we utilize grounded stubs to maintain high interport isolation across an 8-port symmetrical array. To begin, let us review the structural outline of this presentation to see how our discussion is organized. To provide an overview of today's talk, I will first introduce the driving demands behind Wi-Fi 6E and the associated challenges in dual-band MIMO antenna design. Next, we will analyze the single-element radiator design, explaining its physical structure and how we achieve independent frequency tuning. We will then discuss the evolution from a single element to a two-port system, analyzing the decoupling action of our grounded stubs. Finally, I will present the layout, isolation performance, and radiation characteristics of our full 8-port array, followed by a summary of our contributions. Let us start by contextualizing the current wireless demands and how MIMO systems address them. The rapid progression of wireless local area networks has made high-speed, high-capacity, and low-latency communication essential. Wi-Fi 5, Wi-Fi 6, and the recently opened Wi-Fi 6E bands necessitate systems that operate across both 5 GHz and 6 GHz spectrums. To maximize throughput and spatial diversity without increasing bandwidth or power, MIMO technology is now standard. However, implementing dual-band multi-port configurations requires compact radiating elements that can handle complex multi-channel signals while minimizing signal degradation, driving the need for novel planar designs. Now, let us examine the specific challenges faced when designing these compact multi-port antennas and how our design addresses them. When we place multiple radiating elements close to each other, mutual coupling becomes a severe issue, degrading matching bandwidth and diversity performance. While single-band decoupling techniques such as defected ground structures or neutralization lines are well established, they do not easily scale to dual-band systems. Existing dual-band solutions often rely on three-dimensional electromagnetic bandgap structures, air-gap layers, or complex multi-layer metasurfaces. These approaches drastically increase manufacturing complexity, structural profile, and overall footprint, which motivates our goal of creating a low-profile, single-layer solution. To address these challenges, let us inspect the layout of our proposed single-element radiator. Our proposed single-element radiator is built on a Taconic RF35 substrate with a relative permittivity of 3.5 and a substrate thickness of 1.52 mm. Rather than utilizing complex stack configurations or air gaps, we feed the antenna via a probe-fed microstrip line. This line capacitively excites two rectangular patch resonators situated in close proximity on the same layer. The larger patch is optimized to resonate at the lower band of 5.2 GHz, whereas the smaller patch is physically scaled to operate at the higher frequency band of 6.7 GHz. Let us now look at the simulated performance of this single element and analyze how the bands can be tuned. The reflection coefficient graph shows clear resonance modes at 5.2 and 6.7 GHz, corresponding to the fundamental TM10 mode of each patch. The impedance bandwidths successfully span 5.14 to 5.32 GHz and 6.63 to 6.78 GHz, while achieving a stable peak realized gain of approximately 6.7 dBi. A key advantage of this design is the low cross-sensitivity during tuning. By increasing the length of the larger patch, we can shift the lower resonant frequency downwards without perturbing the upper band. Similarly, adjusting the smaller patch length shifts only the upper band. With a functional single element, our next step is to expand the design into a two-port system and analyze inter-element coupling. To scale this design, we first constructed a two-port system, placing two identical elements in the same orientation with a 3 mm edge spacing resulted in poor isolation. To address this, we inverted the orientation of the second element to maximize the physical distance between the active patches and introduced two grounded stubs. This optimization yielded a highly improved port-to-port isolation exceeding 20 decibels across both bands. Let us analyze the exact electromagnetic mechanism that enables this dramatic decoupling. To understand how the isolation is enhanced, we analyze the surface current distributions on the metallic structure. The grounded stubs are designed to behave as parallel LC resonators, functioning essentially as band-stop filters around 5.2 GHz. Because the stub length is precisely 10.5 millimeters, which is approximately a quarter wavelength at the lower band, it generates a neutralizing current. When one port is excited, the coupling energy that would normally transfer to the adjacent port is captured and safely grounded by these stubs, yielding a 10 decibels isolation boost. Using this optimized two-port cell, we can scale the design up to the target 8-port symmetric MIMO array. For multi-channel transmission, we expanded our two-port unit cell into a symmetric 8-port orthogonal array. The configuration arranges 4 of the optimized dual-port elements in a square loop around the quadrants. This orthogonal placement utilizes polarization and pattern diversity to keep coupling between adjacent quadrants extremely low, while the integrated grounded stubs mitigate coupling between the parallel microstrip feed lines. The final integrated array fits a compact footprint measuring just 1.38 by 1.38 wavelengths, with a low profile height of only 0.03 wavelengths at 5.2 GHz. Let us now evaluate the simulated S parameters and overall radiation performance of this 8-port array. Under excitation at port 1, the reflection coefficient dips significantly, indicating excellent impedance matching at both design frequencies. Crucially, the transmission coefficients between the excited port and all neighboring ports remain well below -17.5 decibels in the lower band and below -20 decibels in the upper band. The highest coupling occurs locally between parallel elements within the same cell. To conclude, let us summarize the key achievements of this design and outline our planned future work. In conclusion, we have designed a compact, single-layer, 8-port, dual-band MIMO antenna array that meets the rigorous demands of Wi-Fi 5, Wi-Fi 6, and Wi-Fi 6E standards. By pairing a capacitive feed mechanism with grounded stub resonators, we successfully achieved independent band tuning and high port isolation without increasing the physical complexity or thickness of the profile. Our simulated results confirm a low footprint, high broadside gain, and excellent diversity. Moving forward, we plan to fabricate and physically validate this prototype and explore scaling up to massive MIMO arrays.